Okay, so for our second hour today, I want to look a little bit at errors. We've talked about tolerances and allowances, absolute and relative. Let's talk about errors. If I have a measurement, let's do this. Let's say we have an object that has an actual size of 27 1/8 inch. We take a measurement of it. And we get a measurement of 27 1/4 inch. There's an error in that measurement. Now, we mentioned before, every measurement has a built-in possible error because of the error in the measuring device. But the measurement itself will have an error, sometimes because of the measuring device, sometimes because of human error or inaccuracy. So what we're looking at here is total error, period. Something called absolute error is simply the difference between the actual size and the measured size. Now, it doesn't matter which one's bigger, it's just the difference. We don't care about positive or negative. So I'm just going to take the larger one, the 27 1/4, minus the smaller one, the 27 1/8, which gives us a 1/8 inch absolute error. Does that make sense? The relative error is related to the size of the object, kind of like that relative allowance or relative tolerance. It was a percent. Well, our relative error is the absolute error divided by the actual size. So that's going to be 1/8 inch divided by 27 1/8 inch. Which gives us 0.004608. That's a relative error. Now, depending on the textbook, some textbooks define a difference between relative and percent error. Some define them as the same thing. The percent error can be found from the relative error by just moving the decimal point, making it a percent, moving it 1, 2. So the percent error here would be 0.4608%. So less than a 0.5% error. Is that an acceptable error? Usually, less than 0.5% is usually acceptable. Shake your head, nod your head, both. If you catch me at the right movement, I've got it right. So does that mean an eighth of an inch is always an acceptable error? No. Not always. Because if I have an object that has an actual size of 3, let's say it's 3 5/8 inches, and we measure it to be 3 1/2 inches. What is my absolute error here? Yeah, the 1/8 of an inch. I'm going to take my 3 5/8 minus my 3 1/2. Get a 1/8 inch absolute error. What is the relative error going to be? Will be 1/8 divided by 3 5/8. Which gives us 0.03448. If I change that into a percent error, move the decimal 2 spots, that's a 3.448%. Just under 3.5%. That is most likely not acceptable. So that 1/8 of an inch error was acceptable when we had something that was in the 20-inch length range. But if we're only down around 3 inches, 1/8 of an inch is a lot. It's too big. So that's why the relative error, the percent error, is more useful than the absolute error, because it relates the size of the actual error to the size of the object to begin with. Now in practice, we don't know the actual size of the object, do we? If we knew the actual size of the object, there's no reason to measure it, is there? So in practice, we use that possible error in the measuring device. We assume that you don't make any screw-ups in your measurement. So we're assuming that human error is limited, which we know might or might not be a bad assumption, right? So I'm just going to take a little piece of this measuring device. So looking at this, if I have an object using this ruler, and I get a measurement that I'm reporting at 2 1/8 inches. Now again, we don't know the actual value. If we knew the actual length, we wouldn't need to measure it. But what is the possible error in this ruler? Well, to find that, the first thing we got to do is we got to find the degree of precision here, right? The degree of precision, how many spaces are there between 2 inches and 3 inches? 16. So the degree of precision is a 1/16 of an inch. So that means the possible error would be plus or minus 1/32 of an inch. Now, before I go any further, let's set a standard. Let's set a goal of 1% or less error. Okay? So we've got a possible error of plus or minus 1/32. So we're going to say that our absolute error is going to be a 1/32 of an inch. That's the worst possible case. I mean, it could be dead on. It could be zero error. But this measuring device is giving us a possible absolute error of a 1/32 of an inch. So then what would our relative error be? Well, it's going to be 1/32 of an inch divided by 2 1/8, right? So my calculator, I'm going to put in 1/32, which is 0.0325, divided by 2 1/8, 2.125, 0.01529. What's that? 125, not 25. Thank you. So it's 0.03125, not 0.25, divided by 2.125. So 0.0147. We'll call that. So now we're going to change that to a percent error. Our percent error then would be what? 1.47. That is greater than our 1%. So what that is telling us is this measuring device is not precise enough to measure this object within the error that we want it to be. Now you'll notice here, we did not use the actual length here. Why not? We don't know it. So when we don't know the actual length, we will use the measurement instead. Because we don't know the actual length. And the measurement should be pretty darn close to the actual length at least, so that that ratio or that decimal is going to be pretty close. Does that make sense? Okay. So I want you guys to try one of these in your notes for me. So we report a measurement of 6 3/4 inches. Find the potential percent error in that measurement. So for this one, what was the degree of precision here? It was 1/32. So then the possible error, plus or minus 1/64. We are going to use that as our absolute error. So our relative error is going to be 1/64 over 6 3/4. So that does come out to 0.002315. And as a percent, we move that over 2 spots. That is 0.2315%. And I say go to the 100th of a percent, so 0.23%. So less than 1/4%. That's not too bad. What do you think? Decent? This homework actually is within your page 198 stuff, exercise 4.7 from the tolerances. So we're going to let you work with that. Next week, we're going to talk about resistor color codes a little bit. Resistor color codes. A little bit of electronic stuff. You guys don't need it so much. Automotive needs it. Something handy to have. It's also a good application of all these tolerances and allowances and stuff.